Swayam Prabha. Digital India. Educated India.
Good morning. So in this class, I plan to solve two problems related to absorption in tray towers. And these are exercise problems given in tray ball textbook. And as I do this problem, I encourage you to also follow the steps and do it in your notebook and follow along. So here is the first problem. Please read it through first. Okay, so here it goes. Carbon disulfide, CS2, is used as a solvent in a chemical plant, is evaporated from the product in a dryer into an inert gas, essentially N2. So from this statement, we know that the carbon disulfide is the solute and nitrogen is the inert gas. And in order to avoid an explosion hazard, okay, so we have a mixture of CS2 and N2 and we want to remove this CS2. So the vapor N2 mixture is to be scrubbed meaning absorbed, with an absorbent hydrocarbon oil. So this is the liquid phase, hydrocarbon oil. We don't know the chemical nature of this oil, we'll just call it as a hydrocarbon oil, which will be subsequently stream stripped to recover CS2. So that means this process talks about an integration of absorber and stripper. The CS2S2 mixture has a partial pressure of CS2 equal to 50 mmHg at 24 degrees Celsius. Okay, so this kind of tells you about the initial composition, and this is to be blown into the absorber at essentially standard atmospheric pressure at the expected rate of 40 meter cube per second. The vapor content of the gas is to be reduced to 0.5%. So you can see that the inlet composition is given as 50 mmHg. From there we can get the mole fraction, and then the vapor content of the gas to be reduced to 0.5%. The absorption oil has an average molecular weight, viscosity and specific gravity at 24 degrees Celsius. The oil enters the absorber essentially stripped of all CS2. That means the hydrocarbon oil is pure. It does not have any solute CS2. So that's what this means. And the solutions of oil and CS2, while not actually ideal, follows Raoult's law. Okay. So this sentence is not really important for us, but we can say that this follows Raoult's law, and the vapor pressure of CS2 at 24 degrees Celsius is given, vapor pressure is given, and then assume the operation to be isothermal. So this pretty much defines the entire problem, and there are a set of questions to be answered. For example, we want to know, determine the minimum liquid to gas ratio. For a liquid to gas ratio of 1.5 times the minimum, determine the kilogram of oil to enter the absorber per hour. Determine the number of theoretical strays required both graphically and analytically. And finally, for a conventional sieve tray tower, estimate the overall efficiency to be expected and the number of real trays required. The first two parts are something that you already done for a dilute mixture, where there will be a Henry's law kind of an equation and you know how to do it. Okay, so the first two parts are kind of straightforward, where the third and fourth part is where we have to think about doing it both graphically and analytically. Okay, that's what we're going to do. So first thing I will do is I will make a schematic of the absorber and then make note of things that we know. So here is my absorber. So remember, it is a tray tower. So I will make trays like this, just to distinguish this from packet tower that we dealt with before. when we deal with tray towers, the nomenclature is slightly different from packet tower. Okay, so here we denote y1, x0 here, and this would be yn plus 1. If there are n trays, the inlet composition is given as yn plus 1, and this is xn. And then correspondingly, you can say y1. These are all in mole ratios units. So what do we know about this? The inlet composition is given in terms of partial pressure of CS2, that is 50 mmHg. Okay, so we can say this yn plus 1 is 50 mmHg, and the total pressure is 1 standard atmosphere. In terms of mmHg units, this is 760 mmHg. So this gives you the mole fraction, and this is 0.0658. So I can substitute that here, 0.0658. If I convert this into mole ratio units, that is y by 1 minus y, you will see this is 0.0704. And it said that the vapor content of the gas is to be reduced to 0.5%. So this is going to be 0.005, and you can convert this into mole ratio, and this will be almost same as 0.005. And the hydrocarbon oil is pure, and this we don't know. About the equilibrium line, we are given that this system follows Raoult's law. So we can write this y star is equal to the vapor pressure of A by the total pressure times the mole fraction. And what is the vapor pressure? Vapor pressure at 24 degrees Celsius is 346 mmHg. 346 by 760 times x. So this comes out to be something like 0.455x. So this is the equation of the equilibrium line, straight line. And if you want to write in terms of the mole ratios, you will get this. Now the first part of the question A is to find the minimum gas liquid ratio. So for this we are going to write overall mass balance or material balance, overall material balance. When I say overall material balance, what I mean is I am considering all the inlet outlet streams of the entire tower, not really looking at what's happening within the tower. Okay, so you will see that GS times yn plus 1 minus y1 should be equal to LS times xn minus x0. We know both of these y values, it's mentioned in the problem. X0 is given as 0 because it's a pure hydrocarbon oil. We do not know xn and we do not know this LS and GS. Okay, so in order to find this LS by GS minimum, what this means is this xn that is going out is in equilibrium with, this is in equilibrium with yn plus 1. Okay, and this would correspond to a minimum LS by GS. So what we can do, we can use this Raoult's law in mole ratio units, substitute for yn plus 1 for y star and then get x. Okay, so that is what xn that I am looking for, corresponding to minimum L by S ratio. So this will come out to be something like 0.168. So the way I'm getting this xn is that I'm substituting in this equilibrium relation the value of yn plus 1, and the corresponding equilibrium value of x would be the xn. Okay, so in terms of graphically, what we would have done is we would have drawn the equilibrium line, and then the operating line should be touching corresponding to yn plus 1, and this is how we read xn here. Instead of doing this graphically, I am just calculating analytically, because at this point the operating line and the equilibrium line are touching. So I can relate xn and yn plus 1 via the Raoult's law here. Okay, so if you substitute in this equation yn plus 1, and you will be able to get xn, so that they are in equilibrium. So now in this equation we know xn also now, and then we can find what is Ls by Gs minimum. So this would be yn plus 1 minus y1 by xn minus 0. So it's a mere substitution now. Yn plus 1 value is 0.0704, y1 is 0.005, and xn is 0.168, and you will get this as something like 0.39. So this problem is a little bit ambiguous, because it says determine the minimum liquid to gas ratio. It does not say whether it means solute free liquid to gas or the total gas liquid to gas. Okay, that is not very clearly mentioned. So I will assume it is the solute free molar flow rates, Ls by Gs. But if you want L by G, you know how to calculate that. Okay, so you know the corresponding mole fraction at the entry point, and then you basically use that to get L by G. Okay, so you know that Ls is nothing but L times 1 minus x, and Gs is G times 1 minus y. Okay, so I can say this is at the entry point, so this would be n plus 1 and this would be n, and we know these values. From here we can calculate L and G also. This also can be easily found. Okay, so right now we will keep it as Ls by Gs. So that pretty much answers the first part of the problem, that is the A. And then part B is to find a liquid to gas ratio of 1.5 times the minimum, and then determine the kilogram of oil to enter the absorber per hour. Okay, so in part B, our Ls by Gs value is 1.5 times 1.5 times Ls by Gs minimum. And you will get something like 0.585. So now we have the actual Ls by Gs value. We can actually go back to the material balance here and then solve for actual xn. Okay, so the actual xn should be somewhere here. Okay, so this slope is 1.5 times the minimum. Okay, so you can solve for you'll get something like 0.11. So I can go back to this figure and then mark this value here is 0.111. Okay, so what's the question here? So question B is to calculate the determine the kilogram of oil to enter the absorber per hour. Okay, so so we have got LS by GS is 0.585, but we want to calculate this in terms of how much liquid is used per in terms of kilogram of liquid to enter the absorber per hour. So that means we have to find out what is the gas flow rate. Okay, if I multiply the gas flow rate with this ratio, I will know what is the liquid flow rate in moles, and then I can convert into kilograms. So in order to do that, let's look at what is given about the gas flow rate. It is said that the gas is flowing at a volumetric flow rate of 0.4 meter cube per second. Okay, this is given in volumetric flow rate, and the inlet gas temperature and pressure is given. So using ideal gas law, I can find the density. If I know the density, I will know what's the molar flow rate. Okay, if I know the molar flow rate of the gas, I will know what's the molar flow rate of the liquid, and I have to multiply by the molecular weight of the oil to get the weight or the mass of the oil. So that's the strategy we are going to do. Okay, so first, the volumetric flow rate is 0.4 meter cube per second. Now the density of the gas, rho g, this is actually molar density, is N by V is given by P by RT, and P is 1 atmosphere, so in bars, and the temperature is 24, so 297 Kelvin. Actually it is 24 degrees Celsius, so it will be 301 kelvins. And if you solve this, you will get something like 40.5 moles per meter cube. This is the density of the gas. So I know the volumetric flow rate and I know the molar density. So if I multiply this Q times rho g, I will get 0.4 meter cube per second into 40.5 in the units of moles per meter cube. I will get something like 16.2 moles per second. So this is G, but what we want GS. So GS is G times 1 minus yn plus 1. So I'll get 16.2 times 1 minus 0.070. Sorry, this is supposed to be a mole fraction y. 24. So 273, 290. Okay, so this should be 297, right? Okay, yeah. So the temperature here is let's say 297. Okay, so I'm getting something like 41.0. So you'll get 16.4 here. Yeah. $16.4 and yn plus 1 is 0.06658. So you'll get GS as 15.32 moles per second, and I know that LS by GS 0.585. So you get from here LS will be 0.585 into 15.32. It's about 8.96 moles per second, and the molecular weight is 180. So this becomes 1.612 or 613 kilogram per second, and in terms of per hour, this would be 5,806 kg per hour. So this is answer to part B. So part C is to find out the number of theoretical stages. Okay, so part A, part B are straightforward. So part C is to find the number of theoretical stages from numerical point of view as well as from graphical point of view. So first we will do analytically. So you may recollect that when we have the equilibrium line to be a straight line, and for dilute mixtures we used the analytical expression, the Kremser equation. So that is NP is given as log of yn plus 1 minus mx naught over y1 minus mx naught into 1 minus 1 by a plus 1 by a by log a. Okay. Yeah. So dilute mixtures, equilibrium line is straight line, and the operating line is also straight line, and then the stages are ideal. So if you look at this equation, the only thing we don't know yet is absorption factor A, but that we can find out because we know the equilibrium line slope as well as the L by G ratio. Okay, so this absorption factor L A is given by L by mg, and sorry, LS by GSM. So M is given here already based on the Raoult's law. Yeah, sorry, it's total, is it? Okay, we can do that. So let's see. So we have the slope here is 0.455. Okay, so let us use the total flow rate. And so I can write this as LS into 1 minus, did I use x naught or xn? Okay, so we'll do with respect to the x naught. Yeah. No, I'm actually thinking about whether to use the composition at the top of the tower or at the bottom, because liquid is flown from the top. Should I use x naught or xn? So L is referring to the flow rate, so maybe we can use the top, the one at the top, because that's where the liquid is actually flown in. So again, it's a choice. Okay, there's a little bit of ambiguity here. So I'll say this is measured at x naught, and that's my L, 1 by m, and G will be GS times 1 minus yn plus 1. Okay, I am actually finding the total flow rate with respect to the inlet condition for both streams. With respect to the liquid, I am talking about the composition at the top. with respect to the gas which is entering in the bottom, I am using the composition corresponding to the entrance of the gas. So that's why I am using x naught here and yn plus 1 here. Okay. So LS by GS ratio is 0.585, and then 1 minus this is 0.0658, and m is 0.455, and 1 minus x naught is anyway 0. Okay, so A I am getting something as 1.2. So NP will be log of yn plus 1, it's all mole fractions by the way. So 0.0658, x naught is 0. You can use this, I get something like 6.04. Number of theoretical stages based on Kremser equation. And now how do we do this graphically? So first what you need to do is you have to create this, for the graphical solution you need the equilibrium line and the operating line. Okay. So for the equilibrium line I am taking x values, some x values 0, 0.01, 0.05 and so on. So correspondingly I am calculating this y value based on Raoult's law, and then I am making the mole ratios from the mole fractions, and those are plotted here as a blue line. Even though this line is straight line in mole fraction units, but in mole ratio units it's slightly curved. Okay, so that's a blue line, and the operating line is shown as green here. Okay, so green one here, this point here is y1 and x naught. X naught is 0, so that's why this cuts at the y axis. Okay, so this will be like 0.005, and the other point here is based on the operating line, LS by GS value of 0.585. So y axis somewhere here is something like 0.074 or something like that, and here this will be 0.111. So the two ends are known. So now to construct this staircase diagram, I want to just take this plot. Okay, so here you can use any graphing software or Excel to make these two plots. Okay, these two lines. So this is the equilibrium line and this is the operating line. From part A and part B we know how to construct this. So now we want to calculate the number of equilibrium stages from graphical method. So we start from here and go horizontally and touch the equilibrium line, and I go vertically. So this staircase completes one equilibrium stage such that the outgoing streams here are in equilibrium, and from this point I go horizontally and then I go vertically. Okay, this is the stage 1, this is stage 2, stage 3, stage 4, stage 5. So my stage is so I mean this is not a perfect straight line. So here, so if you do it with a pen, with the scale ruler, you will see that this goes approximately 6. Okay, so if you extend this, if you have 6 stage ideal stage, the outlet composition should be somewhere here, but our operating line stops somewhere here. Okay, so you could say something like maybe 5.5 would be the number of theoretical stages using graphical. So in terms of the Kremser equation, we said 6.04 because we assumed them to be straight line, but actually it is not straight line. This graphical method is a little bit more accurate, okay, because it takes care of all the curvature effects. And so use a ruler and then do this staircase construction with your graph paper that is given to you, and then you will see something close to 6 theoretical stages. Okay. So the final part of the question was to find out the sieve tray. For a conventional sieve tray tower, estimate the overall tray efficiency to be expected and the number of real trays required. So we have found only the number of theoretical trays or theoretical stages analytically and graphically. but to calculate the real trace, we need to know the overall stage efficiency. Okay. So in this problem, the information such as the height of the sieve tower, column height, liquid height, or the mass transfer coefficient, or the interfacial area, none of those details are given. So we are going to use an empirical way of finding the overall efficiency. So for that, I'm going to introduce a chart. It's called efficiency chart. So if you see, this is an empirical chart talking about the overall efficiency. Okay. So on the y-axis, the overall efficiency is given. The overall efficiency is nothing but the number of real trace by the number of the other way around. So number of ideal stages by number of real stages. Okay, that's the overall efficiency. On the x-axis, we have some group of terms related to the liquid properties. Okay, m here is the slope of the equilibrium line. ml here is the average molecular weight of the liquid. Mu l is the viscosity, and rho is the density. So these are all physical properties that we can easily get. Once we know that value, we can look at that plot and then reach out this continuous line, which kind of tells you about the efficiency. So one thing you can note here is that the maximum efficiency this plot shows is something about 60%, and anything less than that. Okay. So for this particular problem, I'm going to calculate the value of this x-axis here, the terms m, ml, mu l by rho l, and then from here read the value of the efficiency. And if I know the efficiency and I know what is the theoretical number of stages, from there I can calculate the total number of real stages. So let's see. So what is this m, ml, mu l and rho l? It is also very important. We have to use the units that is given in this plot. Okay. For example, mu l should be in the SI units, kg per meter second, and rho l should be in kg per meter cube units. Okay. So if you have got the problem in English units, convert them into SI units and use this. So what is the value of m? 0.455, and the average molecular weight is 180, and density is 2 centipoises, right? So it is 2 into 10 power minus 3 kg per meter second, and the density is given in terms of specific gravity as 0.81. So this means 810 kg per meter cube. So I'm getting something like 0.2 into 10 power minus 3 or 2 into 10 power minus 4. So 2 into 10 power minus 4 is somewhere here. This is 2 into 10 power minus 4. Okay, so 2 into 10 power minus 3 would be somewhere here. Okay, but in this problem it is 2 into 10 power minus 4. So that basically somewhere here I should read this value. It is roughly about, it's between 0.4 and 0.5. Maybe we can take 0.45. Okay. Okay, let me just draw that line. So this is the line that I'm reading from this point. So from the plot, the overall efficiency is roughly about 45%, and the number of real trace would be number of ideal stages by E naught. So we'll round off to 6 as the number of ideal stages. So I get something like 13.3 as the number of real stages. Yeah, maybe you can round it off to 13. Yeah, so see, this is a very, like I said, this overall efficiency is an estimate. Okay, so in terms of the exam and answer, you round off to the nearest integer, but in terms of design, like he says, we may want to have one extra tray just to make sure that it gets the, okay, so generally we will say that, you know, round off to the nearest integer. That's philosophy used in answering a question in an exam. but from a design point of view, you may want to give some extra. This efficiency is not the right way to do. If you want to do design, this efficiency calculation is not the appropriate. Okay, so this is just for a rough estimate for academic purpose. So let me just scroll through this problem again one more time, and if you didn't understand any part of this, just raise your hand and ask me. Okay, this is important. I may ask something similar in an exam. Okay, very detailed calculations. Any problem in this particular slide? Yeah, even if you calculate, I think the fourth decimal point is not really significant. Yeah, you get like 0.00502. So yeah, I think part A, part B should be straightforward. I think this is the first time we are probably using this analytical expression to get the number of theoretical stages, and in principle this shouldn't be a problem because we know all the values, so it's a mere substitution and one cannot make a mistake here. And as far as this is concerned, again this has to be done graphically. Okay, so you need to have the operating line and equilibrium line drawn out and then do this staircase construction. But anyway, for the remaining time, I will just put the other question and you can read it and then see how you will solve. So here you can see that this is an equilibrium partial pressure of CO2 over aqueous solution of methanol amine at 25 degrees Celsius are given. So generally the equilibrium line is okay. I will upload this in Moodle, so you don't have to take pictures on that. But so one thing you will see here is that in this problem the equilibrium line is really curved. Okay, because you see the inlet composition is 15% of CO2. It's quite high. Okay, so and in this problem also you'll ask same questions, minimum LS ratio, and then if the actual ratio is 1.2 times this, find out this, and then determine the number of theoretical trays, and then similarly the efficiency. Okay, and so for this problem, after you do the first parts A and B, you'll be able to write the you'll be able to draw the operating line and equilibrium line. The blue curve that you see here is the equilibrium line. Okay, and you can see it's very highly curved, and the operating line of course is straight. So in this case you would draw for the calculation of number of theoretical stages. So this is stage 1. This is stage 2. And stage 3, or maybe 2 point something. So suppose if you extend your operating line, so this would be your first tray, second tray, and this is a tray. So it's somewhere in half, so you can say 2.5 would be the 2.5 would be the number of equilibrium stages. So in this problem, interestingly, you cannot use this Krumser equation because m is not constant, right? Sorry, m is not constant, and so is a. Okay, so what you could do is you can actually in this problem, if you see, they ask you to calculate you see that estimate the average m and then overall tray efficiency to be expected. So to calculate this overall efficiency from this plot, you need an m. Okay, and this m is not constant for the problem. So what you need to do, you have to calculate an average m value over the range of composition corresponding to the operating line. So the operating line composition is changing from here to here. Okay, so over this range of x and y, find the average m value, and that m value you can use to calculate this x-axis value, and from there you can get the efficiency. Okay, That's for the packet column. Okay, this is a tray column. Okay, so we'll stop it here. Yeah.